Hello, lovely humans. Jen Foxbot here. In this episode of Machine Learning Math Mondays, we are going to look at what happens when our machine learning model doesn't do what we want it to do. In other words, when it has a pretty bad output for its prediction or hypothesis function, if you want to get math techie, which we do because it's Math Mondays. Yay! So this problem is called underfitting and overfitting. It kind of can be grouped into just overfitting. So we will look at what happens visually when our machine learning model misbehaves or doesn't do what we want it to do. And we will talk about why that happens, how to figure out that that is happening, and what to do about it. Yay! Along the way, we are going to introduce this concept, regularization, which is really hard for me to say. So I'm going to probably mispronounce it, but that's fine. It's a fun word, regularization. So, yes, here we go. Let's say that we want to figure out height at a person's age. And so we take a bunch of measurements of the height of people at different ages, and we make a fun plot like so, where we plot height on the vertical axis and age down here. And we get a data set that looks like this. Because we are shorter when we are younger and taller when we are older, right? Most of us anyway. But we kind of max out. At a certain age, we stop getting taller, and we just kind of like, boop. Maybe some of us get a little shorter. Oh, that's a little extreme. But something like this, right? You know, we all have different heights, and we grow at different speeds, but in general, when we are younger, we're shorter. When we're older, we're taller. That can be true of pretty much every human. There's always exceptions. Okay, so let's say we run a machine learning model, and the output that we get looks like this. Hey, purple line, that's not right. That means that as you keep getting older, you keep getting taller. That would be terrifying. If I grew at the rate if I kept growing at the rate I was growing in high school, I would be like 45 feet tall. I grew a lot in a very short amount of time, and I was like Betty Spaghetti for a while. So clearly we can look at this and be like, that's not accurate. This will make very terrible predictions on new data. So the purple line, when this happens, when it is a poor fit for our data, this is called an underfit. Another term that you might heard used is called high bias. So in this case, our hypothesis function might look something like this. Well, I drew a straight line, so it would look like a straight line equation for a straight line. So like theta naught, one feature x plus theta 2 is our second feature. But if our data does what we want it to do, our machine learning model does what we want it to do and matches the pattern that we can observe with our brains. Remember, machine learning is not smart. We're smart. We have to train the machine learning model to recognize the patterns that we see. So let's say the machine learning model is like, yay, I did the thing. So this green line is, well, there's not really a term for it. It's just like, this is good. We'll say yay. And so in this case, our hypothesis function might be second order. So something like h theta of x equals theta naught x squared plus theta 1x plus theta 2, where these thetas are feature sets. Okay, and the other issue that we can come across is if our machine learning model is like, wow, I want to connect to all of the points. Let's make a squiggly line. Okay, that's really exaggerated. But when this happens, this is called an overfit. And another term for this is called high variance. So basically, our machine learning model is like, I must include every data point into the pattern, and it gets some wonky pattern that doesn't map well to future data. It misses the whole point. So in this case, we'd probably end up with way too many parameters, way too many features. I might simplify, but let's say we had a polynomial of order 4, so x to the 4th. We'll say 1x third plus theta 2x squared plus theta 3x plus theta 4. A polynomial like this would probably have way higher magnitude, like x to the 32nd. I don't know, I'm making it up. But in this case, both the purple and the orange line, not so good, did not pick up our pattern of how humans are smaller when they're younger. They grow as they get older until they hit a certain point, and then they level off. So this can also happen with logistic regression as well. I'm not going to draw it because it takes me a hot second to draw all of these things, but you can also have an underfit, an ideal fit, and an overfit of high variance with a logistic regression. And you would end up with a similar situation where the underfit simplifies the data too well. It doesn't map to future data, and the overfit is going to try and include every single data point to the point where it misses the pattern again. So how do we deal with this? Well, the first thing you can do to see if your machine learning model is behaving as expected is to plot, just like I did, the hypothesis function on top of your data set. So in each of these three cases, the purple, the green, and the orange lines are our pretend hypotheses, and we've plotted those on top of our actual observed values. So when I visually look at this, I can say, hey, the green line is the best fit. Let's go with that one. This can be difficult for a lot of features, so it might be a little bit hard to do this. But in general, once you have observed that you have an issue, let's say you're dealing with a purple or an orange line, or to say math terms, a high bias or a high variance in your machine learning model hypothesis function, there are two things that you can do. The first one is to reduce number of features. Woo! And by that, I mean these parameters. So you can manually go and do it and be like, in this polynomial, it seems like I could put that one to 0. And just play around with it. That might take a really long time. So if you're really motivated to do it, or if you have a polynomial with not a ton of features, then sure, by all means, play around. And when you do these things in coding, you can write a program to kind of help you do this a lot faster. The other thing that you can do is to use a model selection algorithm. So if you look that up in your favorite search engine, you can see, hopefully something will pop up. I might skip this later on, but if you really want me to cover it, let me know. For now, I'll just mention it. And then the second thing you can do, hey, can you guess? It's in the title. Regularization. Okay, so what regularization helps us to do is, number one, it lets us keep all of the features. So, we're not having to go through and manually deal with those shenanigans. And what it does is it reduces the magnitude or size of each of these. So let's say we start with this parameter value. What regularization will help us to do is it will help us say, okay, this is the pattern that we want. So we really want, let's use colors. We really want this x2 term, this x term, and this x to the 0 term. So what it will do is it will set this at or close to 0. It'll set this at or close to 0, and then it'll keep these parameters. And so it helps us to start with a generic polynomial and apply it to lots of different types of patterns. So that's actually a pretty common method in machine learning, is just start with a giant polynomial and adjust these features, these parameters, accordingly to get the pattern that you want. Okay, So that's overfitting and an introduction to regularization. In the next video, we will look at that in more detail. Please let me know if you have any questions about this or other machine learning topics. I will do my best to answer them. Not a data scientist. I know a decent amount of math, but I will try to address your questions as best as I can. So yay! Oh, also, of course, the whole YouTube-y thing. If you like my videos, please like and subscribe because it motivates me to make these, and yay, that's good. And it also makes me feel appreciated, which is also good. Okay, so I will see you next time, friends. Have a beautiful day. Bye!